FDA structural analysis, FDA thermal analysis, the flow analysis, the CFD analysis that NX can handle, as well as motion simulation. If you go to advanced simulation, there are some tutorials available, right? And I would advise you move through probably the first 3 for the moment, right? But I'll actually have a closer look at this and maybe finalize the set that you should be going through, because there's also the conduction modeling that we're going to need to handle as well. Right, but there's more than enough of a resource that you guys keep going. Tutorial-wise, you're not going to be moving in the software probably for another 2 weeks or so. That takes some time to do. They're all pretty modeling out, step-by-step guides, step-by-step to important parts. Background, you will find that material on here as well. The NX Nastran user's guide. You can go through all the different features of NX and also the mathematical basis for NX as well, which is important. Show why that's not loaded at the moment. Thinking a little bit, but there's a lot of foot for you guys to explore. Right? So today we're just going to look at a simple problem, a different workflow that's associated with structural analysis in NX. First things first, we need to create some sort of a solid model that we want to draw. So we click on File, New, and you've got a whole bunch of options at the top here. That puts you in different modes, so to speak, of the software. Right? So you can be in modeling mode, drawing mode, simulation mode, manufacturing, etc., etc. So we're going to create a solid model, so we need to move over to modeling mode. And what's selected, model in millimeters, is perfectly acceptable. It's very important, of course, to create some sort of a root directory that you can use for development of your model, as well as all the simulation work and the simulation files that are generated. I'm just picking the file I've already created for that, and we can call this file something fantastical. So someone give me a name for our file. You guys need some imagination. Okay, let's call it. All right. So off it goes. We say OK, and it opens up the modeling feature of NX. Right. What we want to do is we want to create a sketch, and we want to extrude that sketch to make our simple part. So you go to the top left-hand corner, click on New Sketch. Right, and it asks you for which plane you want to be sketching on. So you can look at the data coordinate system, right, and select the plane that you want. So I would put it on the YZ plane for argument's sake. Right, the quick pick, which is a feature of NX. Basically, if you select something and your selection is ambiguous, it comes up with options associated with that ambiguous selection. You can see that what is selected automatically is the Z plane. We don't want that. It has given us the YZ plane option, so we can select that. Okay, we've selected our plane, we said OK. and we go into sketch mode. We use the profile feature to create some arbitrary profile that we will use. So basically what I'm making is a little plate, perhaps a thick plate with some holes, for example. Alright, so the profile option allows you to draw straight lines as well as arcs. Starting off with the straight line option, so I'm literally going to go across from there to there, and then maybe there to there, there to there, and then I'll swap over to an arc. Put an arc in place there, and then it automatically goes across back to that straight line option. You can choose, obviously, as you move the orientation, the line goes through the various snap orientations, so we can snap to a vertical line for that, so let's do that. Cross again here, and then over to our original starting point. Okay, press escape twice to get out of the feature. Okay, there's our part, we're happy with that. Let's make some holes, so select the circle option, select the center and radius mode of that. So let's say we want to create a circle right over there. Let's give ourselves a nice big stretch concentration. I'll make it quite close to the edge. Right. Happy with that. You can, of course, change dimensions if you want to. Alright, by editing your dimension. Alright, but I'm happy with what we've got. Just for the demonstration, we're looking at a part that's roughly 120 millimeters long. Okay, so I'm happy with that. I click Finish Sketch. Right, and there's my sketch. Okay, we want to now extrude it into the X direction. So we click on the Extrude command. And the surface we want to extrude is this surface here. Alright, and automatically it goes ahead and does that. Because the x-axis is normal to our YZ plane, it goes ahead and intuitively sets up the extrusion in that direction. And it's extruded to 25 millimeters. Okay, so I'm happy with that. Select OK, and we've got essentially our model part there. Right. So now that we've created the model, we're ready to go with the simulation. And to invoke NX Nastran, we do it via the advanced simulation application. Okay, so click on that. There is a simpler FEA tool called Design Simulation, right? And that's based on a streamlined version of NX Nastran. So it's for very simple analysis, and this kind of analysis would be suitable for us to be using design simulation, but I'll go with more general case advanced simulation. Okay, so click on that, and it takes a while to open up advanced simulation, and automatically brings the part into the simulation environment. Alright, so we've got this part, and we know that using, or we roughly know from the basics of finite element analysis that we're going to discretize this solid, right, with elements. Okay, and those elements are going to enable us to break the complex problem down into a whole set of small, simple problems. Okay, so we need to discretize this solid. Right. In addition, as we will learn in the coming lectures, we need to apply material properties to the solid, so we need to define what the material is associated with the solid. We need to select what meshing characteristics we want, what element type we want. We need to also apply boundary conditions, right? So loads and constraints. Right, so what NX does is it works in a three-part, in a minimum of 3 parts, a 3-step process. But there's an optional fourth step that you can choose if you want to. And that fourth step fits in just after the generation of the part, and it's basically the generation of what NX calls an idealized part. Right. What an idealized part is is it looks at your actual CAD model, right, and it makes a copy of it. And then it allows you to, it's got some tools that allow you to remove features from the model that would cause problems to the meshing process. Right, so those features might be, I might have some text that's, because this is some sort of a product, I might have a text jet, right, that I want to emboss on the surface of this, right. That's great for aesthetics, okay, but in reality the embossment is very, very shallow. It doesn't have any effect on the structural characteristics. Strictly speaking it does, but in reality it doesn't really. So we can ignore that kind of thing. Okay, so we can use the idealization process to remove the embossments, remove that detail. If we had meshed with the embossments in place, right, all of a sudden we're giving a whole bunch of complex geometry for the mesher to have to deal with. Right? And often that results in the generation of meshes, of elements that have poor quality, and we'll talk about element quality in lectures to come. Basically, I'm not going to do the idealization here because it's a simple part. It doesn't have any geometric characteristics that are going to cause us problems with the mesh generation, and it doesn't have any geometric characteristics that we can disregard. Right, so you could, if you were dealing with a complex part in the next phase of this operation, move on to an idealized part model, right, which is copied from the initial part, and you're able to make manipulations to that part, right, without impacting your initial CAD model. Right. Once the idealized part is created, you then move on to what we call a FEM model, finite element model, right? And in the FEM model, what you are going to prescribe is the mesh and the material properties associated with that mesh. And then in the final step, we create a simulation model, finite element simulation model. Right, and in that step, we add our boundary conditions, so the constraints and loading. Right. Once that's done, we can perform the simulation. Right. So at most, it's 4 steps. Today, we're going to proceed with a 3-step process. So we've done first step 1, creating the part file. Right. Step 2 is to create a this finite element model where the mesh is basically generated and our material properties are associated. Right, so I right click on our part file name and I say new FEM. Alright, and I'm happy with all of the default settings there, so I say OK. And alright, the dialog box is going to come up. That's asking for some more information about it. What type of solver are we using? We're using NX Nastran, so the default selection is fine. What type of analysis are we conducting? It's a structural analysis, so that's fine. We don't really need to worry about 2D solids, so leaving that as none is okay. We say OK. Alright, in the simulation file view pane here, right, what we see is we've got our original part file, and we've now got this created FEM file, which sits above the part file. Right. And if we want to go back to look at what our part file is like, we just select Jeff, right click on him, and say make display part. Right. What that does is it simply shows that entity rather than the FEM model. Right now they look identical, so you wouldn't be able to tell the difference. We work in the FEM model, so I go back to saying make that the display part. Okay. Next what I'm going to do is I'm going to create a 3D mesh. Right, I'm going to mesh this body. So I click on 3D tetrahedral mesh up here. It's in the mesh sort of collection of mesh options. First things first, I need to select the body that I want to apply the mesh to. Right, and that body is Jeff. So we click on him. We select it. Right, we've got a few options here as far as the properties are concerned. I will talk a bit more about this in the coming weeks. But right now, that element type, the C-tetra 10-noded C-tetra element is acceptable. Mesh parameters, what element size are we using? This little lightning bolts feature or icon next to the entry field over here allows you to implement automatic mesh or element size computation. So if we click on that, it'll look at the geometric properties of the model and apply some generic algorithm to work out a target element size of 10.6 millimeters. Right? That's what it, as default, sees as a suitable element size. It might very well be that that element size is too big. Right? It's unlikely that it's going to be too small. Okay, so we're happy with that. Then, as we scroll down this dialog box, all right, we want to create a what is called a mesh collector. And what a mesh collector is really sort of an area that your mesh properties associated with a particular type of mesh are collected. Okay, so what you'll find is, because NX is an industrial program, it's been designed to deal with very large, complex parts, right? And often the parts are in assemblies of parts. And often, in that situation, what the mesh you apply to one particular part of region of a part isn't necessarily the same mesh that you want to apply to another part. Okay, so that's what these mesh collectors are. They basically associate mesh characteristics together and allow you to apply those characteristics at a later stage as you work through the model. Okay. So we want to automatically create our mesh collector, and we want to associate a solid property with, or material property with, that mesh collector. So we want to say for this mesh, right, we associate this physical property type, which is P solid, that doesn't change, the default's fine, and we want to associate this particular solid property. Right, so what material is this part made of? Okay. As you can see, at the moment, it doesn't have anything selected, so we can use that outcome to create a physical property, right? And we can use this icon to open the Properties Manager. Okay. For example, if you want to do that, that's fine. And basically what I'm going to do is I'm going to create an option, well, basically create the solid property, but instead of using inherited as the material option here, what inherited means is when you're doing your CAD modeling, often you will select the type of material that your part is made out of for reasons like working out the mass of the part. Okay, so it will associate the density of that material with the volume and work out the mass. So if this option is on inherited, right, then it's going to bring across the data from the CAD model. But we don't have any data, we haven't described that yet, right, so we don't want it to be on inherited, right. We want to be able to select a property or material from the material library. So to do that, we select the icon on the right, and that opens up the material list, and we can select from a bunch of plastics, a bunch of steels, a bunch of aluminiums. But there are also liquids and gases in here as well, because this material list applies not only to the structural analysis, but also to the thermal and flow analysis and sweets. I'm going to choose this steel over here for argument's sake, and I'm going to say OK. Alright, I've now associated the material with the solid type, so I say OK to that. And I've now associated the material and the solid type with the mesh collector. So I say OK to that. Alright, so we've set all the parameters we need to set for the meshing operation. We then click OK, and NX will then go and mesh the part. Okay, so you can automatically see that that's how the region has geometrically been discretized, right? And the elements are tetrahedral, so on the faces you'll see triangular shapes. Right. So we've done our discretization, and we've also assigned our material properties. That completes the second stage of setting up the FEM model. We now need to set up the simulation model. So on the FEM model, we right click and we select the option to create a new simulation file. Right? Again, the default settings are all okay for our purposes here. So we say okay. Right? And I'm happy with all the defaults here, so we say okay again. One thing you will realize with NX, and it's not necessarily a very nice characteristic, but it's just because of the nature of the software. Because it's such a powerful, versatile software, it has a lot of options. Okay? And that's going to probably get you guys feeling confused, but for the most part, using the default settings is completely acceptable for the work you're doing. Alright. So just be patient with the dialog boxes that keep on popping up. Right? And I guess with time, if you carry on using it, you'll really appreciate the value of being able to adjust that sort of information. Right, once again, we ask for what type of solution we want to be undertaking. We want to be using the NX Nastran solver, and the analysis type is structural. So that's fine there. The solution type, as part of the analysis type is linear statics. Right? So the exact solver we're selecting here is NX Nastran's SOL 101 solver. Right? There are other options. Okay? We can look at subcase constraints, a linear static analysis of subcase constraints. What that does is it makes a set of subcases where in each subcase you are applying different loading conditions or constraints. Right? So you can skip through those different cases to look at the analysis from different sets of analyses for those conditions. You can look at super elements, you can look at flexible bodies, linear buckling, response simulation, which is a transient analysis, nonlinear statics, a modal frequency, modal transient response. There's lots of options available to you here. Alright. So what it has is, at the moment, as a default, is perfectly fine, so we say OK. Alright, so what remains now is for us to tell NX where we want the model to be constrained, in other words, fixed, right, and where we want the model to be loaded. So in this case, where should we load the model, where should we fix it? We want to make sure that the stress concentration we've got here comes into effect. Right, so I'm going to say we should load the model on this face, parallel to the face in this direction with the force. And I'm going to say that we should constrain the model over here on this surface and over here on this surface. Let's see what happens with that. Okay, so first things first, we want to create a load, so we go to the load type option and scroll down to see all the options available: force load, moment load, bearing load, torque load, pressure load, nodal pressure load, hydrostatic pressure load. There's lots of options here. Right. All we want is the force load, so we select that. Right. We need to show where that force is going to be applied now. Right. And if we move the cursor over the model, we'll see that we can select the different surfaces independently. Which is exactly what we want. Right? We want to be working with the surface. We want to say on that surface, apply this load to all of the nodes concerned that intersect that surface. So we select the surface. Correct. Again, quick pick comes up because it's an ambiguous selection. I could be pointing to a node, an element, even edge. And what we want is, as we go through the options here, right, it shows you what the option is. So that node is, you can see in the red there, is showing up over in that position. We want the surface, so we go right to the top. That's the surface we want to say select. Okay. The force, let's put on 1,000 newtons. Okay. You can apply different units of force if you want to. We're happy with newtons. And method of application, we can say long vector, fine with that. We now need to specify what vector we are referring to, and the way I'm going to do that is to use the different options here. So this is inferred vector, this is 2 points vector, curved axis vector, all sorts of options. I'm going to use the 2 points vector selection method. right? And I'm going to select this point first. There. I want to select the end point, and I'm going to select that point there, right? And you can see because I've gone in that order from that side to that side, it sets up a vector in that direction, which is exactly where we want the force to be applied. So we say okay with that, and when we've done that, you can see a force vector icons pop up, and they show us that we are putting that force in the right direction. Right, next we want to do some constraining. Right, if you don't constrain the model, you get what is called rigid body motion, and that's basically saying that if I apply a force to something that isn't held in position, right, by a reaction force, that force is just going to push the model in infinite acceleration to infinity, right? And mathematically, that cannot be, that does not promote the solution of the problem, right? So we need to constrain the problem properly. We talk a bit about that in future lectures. So to constrain the problem, I'm going to constrain part up here. And again, you have all sorts of different constraint options. I'm just going to say fixed constraint to keep my life simple. And the selection I want to make is on that surface here, right, as well as the surface here. Say OK, and then all of a sudden the icon showing that the face is being fixed comes up. Right, so in the simulation model now, we've moved from the fair model to the simulation model. We've applied our force, we've applied our constraints. We have everything ready to go for the analysis, so let's go ahead and do the analysis. And to start the simulation, you click solve. Right. The dialog box comes up asking you for a few bits and pieces. We don't need to concern ourselves with that information at this stage, so we just say OK. And once again, NX does its dialog box thing and pops up all its dialog boxes. The topmost one says solution is completed, so we ran successfully. Do you want to review all messages now? Say no. Right. If you say yes, that takes you into files that basically show the different characteristics of the solution. Okay, so if you've got a failure in your solution for whatever reason, you can go into those files and read up what is causing failure. Okay, so from a diagnostic point of view, looking at those files is very, very useful. But as soon as we've had a successful analysis, we are happy to disregard that information right now. Okay, so the simulation ran properly. We now need to move into a post-processing model where we've gone, we know the solve is finished. We've got some results. We now need to see what those results are. Okay, to do that, on the leftmost bar here, we go from simulation navigator down to post-processing navigator. Okay, it's already created, it's already acknowledged that a structural analysis has been undertaken on that simulation file. Right. The results, however, have not been loaded. Okay, so to load those results, right-click on structural and say load. Okay. And that will basically fill that file with all the data that's being calculated. And if we expand on that a bit, we can see all the different options we've got. You can look at displacement, you can look at stress, you can look at reaction force. Okay. Those are all values that will be calculated in the analysis. So let's have a look at displacement. There are various options. We can look at displacement in the X direction, displacement of the node in the Y direction, the Z direction, or the magnitude. Let's select magnitude. Alright. And right click on that and set plot. Okay, there you go. Now what it's showing is the deformed shape. Okay, so it's updated the geometry on the basis of what the solver said to NX about the new positions of the nodes. Right. And that results in the deformed shape. However, very often, especially with very stiff materials and especially with linear static analyses, deformations are very small. Right? So what will happen is NX will multiply the deformation by a scaling factor. Okay, to exaggerate it. And that exaggeration allows you to see exactly where the deformation is occurring. So if we wanted to see what the undeformed shape or what the real deformation is, we right click on post view down at the bottom here under fringe plots. Right? say edit. Okay, and we can adjust the scale there. Right. So if we go absolute, and if we want the scale of, I think it's going to be 1. Test if that's right. Let's just check. Okay, there you go. Right, so deformation is now shown in its actual value, its scales, 100% scale value. Right, so you can clearly see it's very difficult to see that deformation. If we want to have a look at the stress in the structure, we can move away from displacement and go to stress result. Right. And if we move down to von Mises, the resultant von Mises stress distribution, right click on that and say apply. Right, that will give us our stress response. Right, so you can clearly see that the narrowing of those two areas in the model results in some stress concentrations over here and condition over there. Right. The magnitude, the maximum stress, the minimum maximum stress values are shown here. Minimum is just above 0 MPa, maximum is just beneath 11 MPa. Right? So if we're using high strength steel, that really isn't going to be bothering it very much. Okay. Now, just as far as the flexibility of NX is concerned, I just want to show you how you can adjust certain features here. So if we go back in our simulation file view and we select make the FEM file the display part, right? We can adjust the mesh. So we can adjust the mesh size. Say instead of 10.6 millimeters, right? Say we want 3 millimeters. Say OK. It'll then go remesh, right? And then we can move back to the simulation file. Okay, and you can see the new mesh is shown automatically updated. We can then reanalyze. See, it's taking quite a bit longer now because there are far more elements to be solving for, as we would expect. Done. Quite a while actually there. Right, close everything up. Go back to our post-processing, load the new results. Let's have a look at the stress, von Mises stress calculation using the smaller elements. Like that, we're now at a maximum stress of 11.766 MPa, so it's gone up from 10.8. Right. Then, if we want to change the shape of the object, that's fairly easy too. All right. What we can do is we can go back to our select our model. Here I made that the display part, the original model. Right. And we can go back to modeling, and we can edit the sketch. Right. And instead of that point being there, I'm going to make it over there. Right. Finish that sketch. Right. Then move back into application, back to advanced. Right. And then go back to the FEM model, say make that display part, and then the dialog box comes up saying that you've made the adjustment and the geometry has been updated. So that's great. Right. Well, it's recognized the geometry update there by putting that new line in there. I'm just going to find out where the update option is here, because the screen is all squashed. It's looking a little bit into how I had it. Sorry, there we go. That's the icon. It makes the updates on the film part. We go back to the simulation file. You can see that's been geometrically updated. And see that the force is still being applied to that surface, so nothing's changed. We can rerun the simulation. And off it goes. You can see on this solution monitor at the bottom right hand corner, it shows you the time taken for the solution. Shouldn't take too much longer, guys. Okay, there you go. That's been done. Close everything down. And then move over to post-processing, load those results. Have a look at the stress. Right, gone up to 21.76. Okay. So I hope this demonstration has given you a fairly good idea of the basics of NX. It's extremely capable, and this has just touched on its capabilities. Okay guys, so I will see you again next week.